It is difficult to overestimate the importance of light as it pertains to astronomy, because we can't just go out and grab a piece of star or black hole or galaxy or planet even and bring it into the laboratory for analysis. We have to analyze the light that comes to us from these objects. And the light we're talking about is not just visible. We are visible centric beings, but it's electromagnetic radiation of all wavelengths. And it turns out that most wavelengths don't even make their way through the atmosphere to Earth. Two notable exceptions are radio wavelengths. So here's a radio telescope. Radio astronomy is very useful from the surface of the Earth. And then, of course, this is a visible light observatory. So visible light makes it through, and that's good. We all know that because we see things from outer space. But these tend to be the exceptions in the case of the wavelengths reaching us. Light manifests itself as a wave, and we are mostly concerned with that wave nature of the light. So what light is really is just an electromagnetic wave, which is an electric field oscillating in a particular direction, along with a magnetic field that oscillates orthogonally or perpendicular to the electric field, all of which propagates or moves in a particular direction out from the source, in all directions in general. And a few things like wavelength, it's the distance from crest to crest or some other point to the same point a cycle later. So there's the amplitude, and this all moves at a very rapid rate. Well, it's not an infinite rate though. So the speed of light has been very carefully determined, and one way to determine that is even to look at the light that emerges from a moon of Jupiter. So here we have a moon of Jupiter, and when the moon comes into view from the perspective of Earth, it takes a certain amount of time for that light to reach Earth. When Earth is on the other side of the sun, or just a different direction, that would correspond to a different distance. And when that same moon emerges so that we can see it, it takes a different amount of time for that light to reach us. And based on those time differences and the difference in the distance from Earth to the moon itself, the speed of light can be determined. So that's one good way in an astronomical context to determine the speed of light. And it turns out to be 3 × 10⁸ meters per second, very close to that, which is also equal to the wavelength of light, how much distance there is between crest to crest, times the frequency. And the frequency is the number of oscillations, the number of times the wave goes by every second. So if you multiply the wavelength, this would be the wavelength, times how many oscillations there are every second, you're basically stacking up those wavelengths in the direction it's moving. And so in 1 second you would get the distance that it moves in that amount of time. Well, so it's the distance of the wavelength times the number of oscillations, and that'll give you the amount of meters per second that the speed of light moves. And then from this relationship that c is equal to lambda f, the frequency is the speed of light over the wavelength. So here's a quick little graphic of the waves, and if the wave is 1 centimeter, then the frequency is 30 gigahertz, 30 billion cycles per second. Turns out that this is far larger of a wavelength than actual light, visible light at least. If we're talking about visible light, then we've got much smaller wavelengths. But what is shown from here to here is that if you reduce the wavelength, right, so we're going from 1 centimeter to 1/4 of a centimeter, then if the wave is going to move at the same speed, then there has to be 4 times as many oscillations of the shorter wavelength to go the same speed as the larger wavelength. And the speed of light is a constant, so no matter what the wavelength is, it all moves at this same 300 million meters per second, or 186,000 miles per second. But This shorter wavelength will also result in a greater frequency, 120 gigahertz. Turns out for actual light, the frequency is on the order of 600 terahertz, and that's 600 million cycles per second. So that's an incomprehensibly fast speed. But in 1/8 of a second, a beam of light would travel around Earth. So you can imagine these little tiny oscillations of light, which are on the order of nanometers, less than a micrometer, invisible in extent to the naked eye. It would have to oscillate up and down so fast that in 1/8 of a second there'd be enough oscillations to travel all the way around the Earth, even though the distance over every oscillation is less than 1 micrometer. So that's hard to wrap your brain around. But 600 trillion oscillations would have to take place per second in order for it to do that. So it gives you an idea of the speed of light and just the incredibly incomprehensible fast rate at which it oscillates. Wavelength has to do with color. We'll specifically point out the visible part of the spectrum. But the entire electromagnetic spectrum shown across here, we have frequency on this scale going up in this direction, which is inverse to wavelength. Wavelength increases in this direction. In any case, there's a huge amount of variation in frequencies and wavelengths. In fact, if you notice, 10 to the 0 is 1. Over here is 10 to the 24. So it's showing 24 orders of magnitude of wavelength or frequency. You can use those terms synonymously. Visible light just is a little tiny sliver here of the whole thing. You look across here and you go, well, it looks like visible light maybe encompasses, oh, I don't know, a 20th or a 30th of the entire visible spectrum, until you realize that the amount, the value between each one of these scale markings is a factor of 100. Not just a number 100, but a factor of 100. So 100 times more for each one. So this is an incredibly logarithmic or compressed scale. And it turns out if we could take the entire electromagnetic spectrum and stretch it out from the Earth to the Moon, 240,000 miles, then on a linear scale, the visible spectrum that you see here would just be 10 centimeters of that 240,000 miles. So this is very important to us humans, but it's almost insignificant in terms of the entire span of the possible wavelengths associated with electromagnetic radiation. And that's really, really something that should not escape you too easily, because astronomy is interested in all the wavelengths, and information from all these wavelengths is useful in principle to the astronomer and gives us different amounts of information, different kinds of information for different wavelengths. It turns out that light has other characteristics than just acting like a wave. It also can act like a particle. And this historically has given physicists in the early 1900s lots of headaches, including Einstein, who helped us sort it out. Turns out that we can talk about light as being made of photons. Photons can be thought of as, well, you can think of them as particles, and they're little packets of energy, but distinct from the way we would think about a wave, which isn't really a physical object in any particular point, but a photon can be thought of as that. And the energy of a photon is this equation. Well, h is Planck's constant, c is the speed of light. But the important thing here is that the energy of a photon is inversely related to the wavelength. So as the wavelength goes down, the energy goes up, and vice versa. So we have the visible spectrum, 400 nanometers to 750 nanometers. So we see that the energy of blue or violet light is about twice as energetic as that of red light. Experiments can be done to show that if you shine light at some material, if the energy is sufficiently high, it'll knock electrons out of the material. It's called the photoelectric effect, and Einstein actually received a Nobel Prize for this work. So there's a lot to it, but the bottom line is that if you have light of say red, and it's not enough energy. Here's an energy value, 1.7 electron volts. Potassium needs 2 electron volts to eject an electron. You could beam 1 billion of these. No matter how intense the beam was of red light, you would never knock out any of the electrons. Green light, having greater energy, and blue light, having even greater energy, will knock electrons out. And all you need is a single photon. 1 billion photons of red won't do the job because there's not enough energy in the particles of light to do the job. Well, Schrödinger put together the mathematics to describe the wave-particle duality of light. So if you're familiar with that, you'll appreciate this joke. If you're not familiar with that, you are now in part, and so you can still appreciate the joke. The electromagnetic spectrum and atmospheric windows, I've already alluded to that in the first slide, namely that not all the wavelengths make their way to Earth. In fact, what this graph shows is at the various wavelengths, we have very short wavelengths, gamma ray through X-ray, ultraviolet, visible, infrared, and radio. This shows the depth to which that radiation makes it through the atmosphere. So you see it doesn't get all the way down. It doesn't get all the way down. Now we see, of course, visible light makes it all the way through. And then on the other side of visible is infrared, and it tends to get through also if it's near infrared. But far infrared, well, you can study it with high altitude spacecraft, but in general, doesn't make it all the way down. Radio is the other window, so we have our radio telescopes. So you see that most of the wavelengths are not accessible to us with instruments here on the planet. So what do? Well, if you want to investigate the other wavelengths, you put spacecraft out there, satellites. So we have the various satellites that have eyes tuned to different wavelengths. So that's how we do it. Get out of the atmosphere of Earth, and even visible light at that point, the Hubble Space Telescope, is wonderfully more efficient and more useful without having to look through the distorting effects of the atmosphere. Just to give you a basic idea of the different wavelengths and how we can view them, the next few slides will show the sun. Here it is in visible light, certainly filtered down so it's not so bright. And this is just how we would see it if we properly dim the light so it's not blinding us. In this particular image we have the International Space Station that just happens to be transiting the sun at that particular moment. We can take images of the sun through various filters that only allow certain colors through, like blue, green, yellow, or red, to bring out the particular information and features of the emitting body, in this case the sun, at those particular wavelengths to the exclusion of the others. Here's the sun in infrared. So this is the infrared sun. We know it's putting out infrared because we can feel it. Not all of the infrared, but some of it. And it's definitely showing different emission characteristics than the visible. And then, of course, that infrared, which we don't see, is translated so we can see it on the screen. So what you're seeing is a translated image of the actual infrared light itself. Here's the sun in ultraviolet light. That's pretty wild looking. And here is the sun in X-ray. So even in the very energetic X-rays, we have emission from the sun. And here's an interesting one, hydrogen alpha. Don't know what that is yet, but basically hydrogen gas, which the sun is mostly consists of, has its own emission characteristics, and this is observing the sun through that particular wavelength of light. Remember, when we use the word light, we're talking now about electromagnetic radiation. It doesn't have to be visible to the human eye.